Awesome. Hello, everyone. Thank you so much for all the hard work that you put into your challenges. And going through the repos, it was awesome to see all of your submissions and the teamwork that made them possible. These hackathon projects can go on to become more than just 24-hour projects, and we're really excited to give a few of our teams a chance to present their hard work. So without further ado, I'd like to give the floor over to the Avocados with their project.
Hello, everyone. Well, this is our presentation where the title of this project is Quantum Pathfinder, the Vehicle Writing Optimal Solver for the team Avocados, for Alejandro and Alberto. This project is from the Amazon Bracket Challenge.
Okay, well, this Amazon Bracket Challenge, try to that we present something related with Nest devices. Then one of them, or the most useful solution that we can present, is optimization. Then we found a problem that is interesting for the community and can be useful to present here. And this is the vehicle. Well, we call this the Quantum Pathfinder, and this is a representation of the vehicle routing problem. This problem we can represent in way of a cubo or a quadratic unconstrained binary optimization problem. And we will solve this problem using QAOA. The problem consists on, we have a deposit and we want to deliver some package to some customers. Then what is the best route that we can use to deliver those package? And yeah, that's mainly, we use QAOA and we use a classical solver to compare both of them. And we present a new tool for encoding CPlex problems into bracket and penny lane. This is the cost functions. This is as simple as we have some routes that we could cover, and we want to minimize the costs associated with going through those paths of those routes. And the nodes correspond to the customers. And we have like a central deposit, and we have a number of vehicles that can cover the routes. Then it's like finding what is the route for each of the vehicles to cover all the customers. And we have a set of constraints, and this is useful to represent in something that we call CPlex, that is a classical library from IBM that allow us to represent the minimization of the objective function and some restriction that we have here. The objective function is like in terms of binary variables, and yeah, we can represent, this is the way that we can encode the problem, and we have the file that we can generate the problem. We have the minimization function and some restrictions that we want to accomplish, and we have a set of bounds and the number of binary variables that we have for this problem.
So continue with this idea. We started with one graph, starting with one node. It means it's the deposit, and the other is the destiny routes. So for this, we can rewriting this in a quadratic program, and we can use it for CPlex for the cubo. And the challenge in this project, the challenge for this 24 hours is how to build the QAOA in penny lane using this input. The most difficult part is how to obtain different information that implements, well, exists in the implementation now in the library penny. So we started all the codification. We identify different backend like noise model, simulation, and possible real hardware using AWS bracket. And the solution given us in 3 different methods is from IBM, from Kiskin, penny using Amazon bracket, and the CPlex classical solution, and we identify the solution with different colors in the graph. This color represents the optimal solution.
Okay, but we have to encode this problem, And yeah, we have a reduced number of qubits. For example, this simple problem of only 3 customers and one deposit, like use 12 qubits. And we tried this with using Ziplex, and we find the optimal solution, which is what we show here. But also we encode this using QAOA and Cobila, and with just a small number of iteration, we can find the correct solution for the same problem.
And how to check this proposal of the QA is correct? Well, we're checking with the cost function. Depends on the different iteration. It is in 27. One diff of the Hamiltonian P equals to 1. We check in the initial cost decrease in negative values. So then with more probability, the step represent the optimal solution.
Okay, and about the implementation in AWS, we use a penny lane because we can use the backend from AWS and penny lane, and we encode the whole QAOA problem into a penny lane circuit. And with this, we create a cost function based on the Hamiltonian that we are trying to encode. And we get the result of the set of probabilities. But we stop here because we couldn't finish completely. But the next step is picking the correct solution from the distribution of probabilities that we get back from the AWS the backend, and with this giving the solution as we present here above. And some of the conclusion is that we really can compare these classical and quantum algorithms, and we get the same correct solution for both of them. And with just one repetition of the code that we present here as P, that is how it is called in the QAOA algorithm.
Other conclusion is we can generate a new solution from the library PNL for the QA problem using the input, the QO, and we can extrapolate with different applications, not necessarily this for this presentation. We can generate for other things with different backends, not necessarily PNL. We can use Amazon, even it could be the same for IBM backend or Rigetti or the other ones. And we are considered with this, if we can connect with real hardware, we can try to mitigate using the connection from AWS and PNL with Mythic library to identify with CNE or zero noise extrapolation and try to mitigate the noise in the real hardware using this proposal solution.
Thank you.
That's all.
Thank you so much for that wonderful presentation. Wow, that was so thorough. I'm like continually impressed. I feel it'd be impossible for me to come up with something like this in the amount of time y'all had. That was absolutely fantastic.
Thank you so much.
Yeah, absolutely. So now I'd like to hand it over to Q Snapjack to present their project.
Can you hear? Can you see my screen?
Yes, I can. I can see you fine.
All right. So my project is, well, our project is not, sorry, our project is not nearly as sophisticated as the last one. Our team was 3 high schoolers and a first year undergrad student. So it's a bit messed up, but so we developed a variant of blackjack using quantum properties. So we found for the IBM challenge, we were asked to develop some sort of game which involved players being able to sort of compete against a quantum computer. And so what happened was so we began with an ideation/conceptualization phase, where our initial motive was to implement a probabilistic yet numerical game, looking at quantum properties for an added enhancement. So we found blackjack, and we thought, okay, if we can apply quantum, if we can sort of have a quantum twist on blackjack, that could be a good way of approaching the challenge. And the reasoning behind that was mainly blackjack is both numerical, as in you have to reach 21, and also there's a lot of probability involved because it's a card game, right? So that's the main reason why we chose blackjack as the way to go. And then we went into some research and we found this specific paper, which was a quantization of blackjack by by Y. Mura and H. Wada. This paper was a bit of a mess in terms of it. I think it was directly translated from Japanese, so it was very hard to understand. And it was a very deep and thorough paper for people with not as much experience in quantum computing as our team. But we developed an understanding of some of the quintessential stuff. So this is how they represented the game in their paper, and this is what we tried to implement. So what they did is they defined a set of states. So they defined the state of the deck, the player's hand, the control bit, which is actually 3 bits, the player's strategy, dealer's hand, and dealer's strategy. I failed to mention, by the way, they were working with something called Snapjack, where Snapjack is I've not mentioned it. The Snapjack is a variant of blackjack, but instead of using 52 cards, it uses 8. The way they worked with the deck, the player's hand, and the dealer's hand is a sparse representation. So if a card was in the deck, then they had 8 qubits, and the qubits were all 0 if there were no cards in the deck. And if a single card was in the deck, then the qubit at that index was 1, etc., etc. And this meant that you couldn't reasonably do an actual blackjack game. And even with their implementation, they used 37 qubits with Snapjack, which was quite crazy, and we could not run that either. So we had to even downsize it even more. So our game was technically Sorry, is it Snapjack? Yeah, it's Snapjack, or yeah, Snapjack. But yes, I'm fumbling around a bit. But the main part of this was the, can you see my cursor?
Yes, I can see your cursor.
Okay, so it was mainly the this X or I and this hit operator here, and then there was the yes. So this was the main component. This is the main part of the player's interaction with the whole thing, and then this is more of the dealer. In our case, this was the quantum computer. Well, kind of, but this is the dealer's actions. So what we did is, if I can I move my slide? Yeah. So the paper, as I just said, it uses sparse representation, so 0, and then also it had strategies. So if you look at the previous slide, if you look at the previous slide, there's a player strategy and a dealer strategy. So this strategy is a 0 if the player will hit, and a 1 if the player will stand. Oh, sorry, no, the other way around. 1 if the player will hit, and a 0 if the player will stand. Same thing for the dealer. And it's initialized as 0 for the player and 1 for the dealer. Then you apply a NOT gate, or an X gate, sorry, to the player's strategy if you want to change it from a 0 to 1. So the player can choose to either stand or hit, just like they can in normal blackjack. And the way it works in this quantum representation of the classical game is you use an X to flip the gate. But there were many issues. So there were 37 plus qubits needed for their implementation. For regular blackjack, you need about 160. So we had to simplify it so that it would only use 4 cards, the ace, 2, 3, and 4. Oops. So that we would be able to reduce the number of qubits to less than 20, which made the game a bit less playable because suddenly you didn't have much of a game left because you had to just remove so many cards. So that was one of the key problems that we faced just because of how many qubits this paper implemented it with. And then the strategy, so the novel property of this was the new property, which was the quantum twist, was that right here in the, I hope you can see my annotations, but right here in the
Yes, we can.
XOR, yes, okay, thank you. This X or I, instead of limiting this to just X and I, they enabled it to work for the set of 4x4 matrices, X, I, Z, and so X, Y, Z, and I, which means you could essentially entangle the dealer state and the player strategy, because you could entangle the player strategy. So that allowed for some twists in terms of quantum things. I just don't want to go into deeply because I'm waffling a lot right now. And I'm a bit tense, but sorry. So then the biggest problem, aside from the fact that this would have needed like hundreds of qubits to actually work, is the hit operator. So the hit operator was how they actually processed hits in terms of taking a card from the deck. And because, of course, you're not going to actually be able to just remove a card from the deck. So this involved using a controlled swap gate, which is actually really difficult to figure out just from the image alone, which essentially checked if the card was present in the deck. And if it was, then it swapped the player and deck states around, and it used a deck copy for some strange reason. Yeah, and yes, and I think that's about it. Sorry.
Oh, no worries. Sorry. Is that, yeah. Is that, you mean that's about it? You don't, there's nothing else you want to say?
I'm not able to. Okay, one sec. Yeah, that's about it.
Okay,
Sorry.
sweet. Wow, that was absolutely wonderful. You know, I want to assure you that I don't think you were waffling. I think you were very much more eloquent than I could be spontaneously over Zoom. I really appreciated the presentation was very thorough. I also wanted to comment, I love the way this idea came about, this connection between the probability and quantum information to a probabilistic game. And I think that like going about this by reading and analyzing a paper is such a wonderful way to be able to make a contribution over like just 24 hours. So I really want to commend you for this project.
Thank you.
All right, and then next, and this is going to be our last group, I believe, who's presenting today. I would like to hand the floor over to Physics Feed to tell you about their project.
Thank you very much. I'm sharing the presentation in a moment. Could you confirm you see it?
Yes.
I'm not sure if you see the windows here, the Zoom windows. Yes, no?
I can't see the Zoom window. I can only
Okay.
see the presentation screen.
Excellent. So, Gargi?
Hello, everyone. Welcome to QC Act 2022. This is Physics Feed, and we took up the QGrade Open Cousin Parser Challenge. In this challenge, we had to build a program that converts Python quantum circuit objects, which is built in an AWS bracket, into sets of instructions in the form of logic gates, which the original circuit was composed of. Next slide. So who are we? We are a team of 4 belonging to very diverse backgrounds. We have Nadeem, Saket, Vailala, and me, Gargi. And now Nadeem is going to take over and he's going to walk you through the technical details of our project.
Yeah. So am I audible? Ben?
Yes, we can hear you.
Sorry, pardon? Yes, I can hear you.
Okay. So yeah, we have presented the solution to the challenge of a parser challenge. So what we have done that in that parser you have seen that parser compiling a quantum compiling language. So it will pass to a Pythonic scripts to parameterized gate sets. So what we have done is the parser is challenging the Pythonic scripts to parameterized gate sets. So it's suppose if we have a hum dot gate, if we have a C dot gate, okay, so these are the standard gate. So what we have done, propose a general case here. So in that general case, we have all standard gates and we easily pass from it to Amazon bracket to open chasm. Okay. So first of all, we have tackled the Amazon bracket challenge. In that we have the Amazon bracket challenge. Okay. So in that we have taken the objects and we have turned it to the Python scripture. We have done the Python instructions for the general case, and we have set up some instructions and then turned into an open chasm strings. So what we are doing taking the standard gates and converting into the strings. Suppose you have seen that JSON. What the JSON is doing? JSON is doing for the it's a special case. Okay, suppose we have a C node gate. So, okay, so it's a JavaScript object notation. So it's a very it's doing sorts of C node get. It's assuming out CX only. Okay, it's so JSON. We are using JSON for specialized gates only, and we are if JSON not used, then it's for general case. Okay, so we have used Amazon bracket in the Kubernetes lab environment and taken it to the Amazon Open Chasm language. And for that, can you please scroll up, Violeta?
Yes, I'm in general workflow.
Yeah, general. No, that yeah, about that general work, about that. Yeah, about that. Yeah. So we have not done yet measuring the parser. Okay, so it will be coming soon. We have taken the general case. We have taken the JSON file through the parsing, and here is the documentation. So we have well documented all the gates. Okay, so if someone is from another parser language, if, there's another language, so it will not be problem. Mostly it will not be problem. And documentation, we have well documented all the gates. It will be passed to a open custom language. Yeah. And we have also very specialized gates also, like VI, TI, rather than basic gates, Humdard and COut gates. Yeah. We can, yeah. So I have explained it also. Now I over to you, Saket. So Saket, please.
Thank you, Nadeem. Could you send it over to the next slide, please, Violeta?
Of course, here.
Thank you. So we'll just go a little bit more into detail about our transpiling structure and how this process was implemented. So here we have a little example of the JSON script we whipped up. As we can see, some of these gates are special cases, and we considered them so because the naming structure on Amazon bracket and the naming structure on OpenChasm were different. As you can see, for CNOT, Amazon bracket spells the gate as CNOT, whereas OpenChasm uses the capital C, capital X notation for the gate. Similarly, the V gate which is the square root of the X gate, was called SX, and all the inverse gates ended in DG in OpenChasm instead of I. And since there were a limited number of special cases with which we could have simply just done everything, we decided just to throw everything into a JSON, import that into Python as a dictionary, and just kind of go with the flow on that one. The first thing we did when we got the input is that we took apart the input, which was a circuit object. Now, the circuit object stores information quite literally in chronological order of the gates that act upon the qubits. So an example of that would basically, could you go to the next slide, please? Sorry, one after that. One more. Never mind, I lost my ordering. So an example of this would basically be, can you just go back, please, Violeta? Sorry. Yes, sorry. An example of this would basically be if we had a circuit with a Hadamard gate on the first qubit and then a CNOT from the first to the second qubit, it would have an operation called Hadamard with a qubit next to it, qubit 0, since Hadamard acts on the first qubit and the qubits are 0 indexed. After that, the second operation would be listed as a CNOT with 2 qubits next to it, qubit 0 and qubit 1. Now, what we did in this function is we basically took the circuit object and picked it apart and essentially pulled apart all the operators and the sub-operators and then lined them up so that each gate was one entry in a new array that we outputted. So for a circuit with multiple gates, we would make not just the gate itself, but the gate and the qubits on which it was acting, one entry, and then separate entry by entry and return the array of all entries. After this, we went out to the outstring function where we inputted all those entries And for each line, as I mentioned earlier, we would have, for example, the Hadamard gate with whatever inputs it required, and then the qubits that it was acting on. So first we had to separate the name of the gate. Then we had to compare the name of the gate to whatever our JSON file said, because that's our translation from bracket to chasm. And then after that, we had to pick apart which qubits it was acting on. So we had to call those variables and then format them in a way that was readable in OpenChasm. And we returned those as strings. And we also had a second return parameter, which was an integer, maxi. Maxi is basically the maximum index number of any qubit that was in the operation, aka the number of the highest qubit. So maxi plus 1 in theory is the number of qubits that would be initialized at the start of this operation. And now for the main logic circuit to chasm, we essentially started with a circuit that was input into this function. We ran it through our circuit to list function and then took our other function, which the other function I believe was called outstring. And we put both of those together, slapped together a header, OpenChasm 2.0, include the library with a bunch of gates that aren't standard. And then we registered the qubits, string of max plus 1 being the maximum number plus 1, which is the number of qubits, and then the output we had, which would give us, voila, the output in OpenChasm, easily readable and easily executable.
Okay, so now here we can see a example in order
Is
to
Ivan
put
only talking about the project, or is someone else going to be supporting him?
sorry. Do you hear me?
Yes, I can hear you all right.
Okay, should I continue, or this was a question? If you have any question, we can answer them later. That's okay?
Apparently it was accidental. I just saw in the chat.
Okay,
No
okay. So to put all the pieces together, this is an example circuit. I believe you can see my pointer, my mouse. This is an example circuit written in Amazon Bracket. It was actually in the unit tests in order to see if our project actually works. And this is an example OpenChasm output for it. As Stoka mentioned earlier, we need the number of, we actually define the version of our OpenChasm. We include the needed libraries. We say how much quantum register we will need, and then we apply each gate individually to the specific qubits. And this is actually the intermediate representation that should go further to the compiler. So here's a live demo. Okay, I will just go through all the cells. Okay. Oops. Okay, so here is, again, all the pieces are together. All the stages that were mentioned are in here. You can check out our GitHub. It's called, it's fork of the QC challenge for Kubernetes on Vocaba Java. And here we can run the unit tests in order to show that all the cases that were given to us are actually running, and they're running pretty well. So that was from us. If you have any questions, we would like to answer them. And thank you for your attention.
Wow, that was fantastic. Thank you so much for presenting. Yeah, like I said at the beginning, that was quite an amazing slide deck. I love the way that your team managed to work together on this problem. I think the collaboration is fantastic. And it represents kind of the best collaborative work that can come out of an online event like this. And I also want to like commend you for addressing such an open problem and then treating it with such detail, because that can be really hard when, you know, some projects really have a guide rail for how you can proceed. And, you know, when you don't have that, I think it can be more difficult. So great job. And thank you for your presentation. And lastly, I'd like to pass it over to Humongous to talk about their project.
Hello. Can everybody see me all right?
Yes, we can.
Okay, cool, wonderful. Hello, everybody. I love seeing everybody's presentation. That was very cool. What I'm here to talk to all of you about is the project we participated in, the steps we took to conclude, to move forward with our project, and what we found interesting about it, and our conclusions at the end of our findings. So let me start with what exactly we aim to solve. If you can let me pull my screen.
You need help?
No, I wasn't sure whether I could pick a specific screen. Let's see. This was a bit last minute. Before I get to the slide, I thought I'd at least say something that was a little bit more as to how we got to where we are with the project, and that is our inspiration. You know, like every good vector has a basis state. It has a set of bases. So basically, we were trying to solve something about this idea that Turing machines imply complexity. This complexity can be described as being a function of time with respect to certain parameters that the space belongs to. And in this example, we went ahead and found an example of a 2 to 3 state machine that allowed us to iterate over some test data in linear time, and such that our diagram belongs to the field. Our diagrams really do belong to the field of polynomial calculus, this idea that one of the biggest applied fields in calculus today is to find out the nature of fractals and the nature of what exactly does it mean for there to be computability with different many parameter spaces. So we took all this complexity and we made it simple. We basically asserted there to be, I don't know if you're seeing the screen, we basically asserted there to be, in our brainstorming process, that A Kronecker sum X, such that X is our is the operator with which some kernel A, some matrix A is operated against.
Yeah, I apologies. I think I don't know, Yvonne, you had a teammate here, I believe.
Just a minute. Oh, a teammate. What did you say?
Sorry, your connection was breaking up.
My connection's breaking up. Okay, I'm sorry. Public Wi-Fi. Sorry about that. But anyways, my point. Can you hear me okay? It is
Yes.
fine now. Wonderful. Wonderful. I don't mean to. Yes. We had been looking towards finding some connection between our entanglement entropy, such that, for example, we would be given one state, one total value, and we would subtract that from a 2-qubit system in 4 space. Each space would represent a 2-qubit system, so that the Turing machines and the 2-qubit
Hi, Yvonne.
Hello.
Hi, sorry. Okay, I'm really sorry for the I'm really sorry for the issues. If you could, I've enjoyed hearing your. If you could wrap up, that would be fantastic.
Let me at least conclude our findings here.
Definitely.
Yes. Oh God. Just a minute, please. Just a minute. Okay, good enough.
Yeah, Yvonne, do you think you'll be able to wrap up your presentation?
Yes. Give me
Okay, awesome.
just a few minutes, please. At first, our initial. Can you see my screen? No, you cannot. Hold on.
No.
Let's see. chroot, dft. No. Walk. Dev.
Sorry, can you would you mute yourself while you're pulling this up?
Am I muted?
No, you're not muted.
Oh, yeah. I'd like to wrap this up, of course.
Maybe you could share what what did you learn from doing this project?
Yes, of course. Allow. Hi. Can everybody see my screen? Can everybody see my screen? I apologize for the disconnection.
Yes, we can.
Okay, wonderful. So basically, my point being, for a given 2-qubit system state, so for a 4-state system with 2 qubits, we're given a super polynomial time that speeds up our process for some given bounded polynomial. So basically, so for the greatest upper bound and the supremum and infinitum, we're given that the ratio between these two is some time complexity that we can use to distinguish just how much optimized, just how much quicker our algorithms can be. One way this is done in polynomial calculus is with encryption and error code correction and things of that sort. We sought to look at images of fractals. So for example, as you can see, this is the character in Among Us, where such that each image is some entity within an orbit trap, and this orbit trap is an area where if we have a z for I indices, if we have a z for I, we're given a z squared function plus a constant that is iterated over many times. In this case, it's a Julia set. With in fractal art, we take to have an orbit trap, and this orbit trap allows us to iterate these images over n many times. And the significance of this image is that it provides us a challenge with which to find some algorithm that can quickly speed up the time that any other image processor would have very great difficulty attempting to look for all of these different Among Us characters. So then, which leads us to questions of, for example, one great application of a 2-qubit 4-state system is iterating over a given matrix of elements, where, for example, we take something similar to a convolution or a filter, a masking filter. If you've ever used Photoshop, you'd understand that given a certain edge detection, we can apply some algorithm that allows us to detect different areas or different lines with a given 1 or 0, or with a given binary operation. In this case, we have a binary black or white operation. We sought to keep it simple and reduced our binary operations for a given FQRI system to that of a Dirac to the Dirac operator, which is given to be delta ij, which is also the norm, the square of the norm, where a given operation whose diagonal is summed gives us the trace, and that also tells us, this also proves this square norm operator and Dirac delta function for a given pixel. We unfortunately did not have enough time to go through practically all of the different iterations of the Among Us. So
Hi, Ivan.
Yes.
Can you show us the presentation, our presentation, please?
Hi, Karya. Yes. Of
Yeah.
course.
Okay.
So
It's right there. Yeah.
so that motivates all of that theory as to how we approach the problem leads us into this section. So in image processing, one application of image processing is the Q-Sobel operator. It's very similar to, well, in this case, we use the FQRI, but that's based off of the Q-Sobel operation in the classical sense. And it also is similar to many other forms of edge detection, where the point is to find the difference between a 1 and 0 value. And so, let's see. Oh. So, oh, sorry, I press play. What we sought to do in this example is encode our grayscale image of some given image. In this case, we in order to make the contrast very clear, we took an 8x8 image of some arbitrary ratio of black and white pixels with which to iterate over and create different time complex systems so that we can better understand the nature of time complexity for a 2 Turing state system and its QBP equivalent, where we take QBP to be this polynomial that describes some n given amount of parameters and how that is differentiated over our time complexity as the number of parameters increases with regards to some function. And this image is an excellent example of that. Sorry. So what we took, for example, was a very large image of the popular game Among Us, and we took an 8,000 pixel image and found that the contrast between the two well, we created a basic classical algorithm that would iterate over each pixel, find a black or a white image, and then calculate the difference between the two of them. So for this given image, most of the background was black, and there were because it was space, where the Among Us character lives in space. One moment, much like this image, and oh God, and given that 8,000 pixel image, we were allowed to compute for the n many pixels in order to obtain some difference between the two pixels, and so this requires iterating or scanning horizontally and scanning. So with respect to the horizontal axis and the width axis. And it is actually computationally intensive to do such a task. And I tried this locally on my computer. I got roughly 38 seconds in order to calculate something, this arbitrary algorithm that can differentiate my black and white pixels in linear time, as every single pixel is passed through the algorithm only one time. We can then assert it is in ON time.
Hi, Yvonne. Thank you so much for how thorough you're being with this presentation. I really appreciate it. To respect the time of the other people, would you mind moving to your conclusions and just letting us know, like, what was the most important takeaway from your project?
Yes, of course. Pixels. So let me just move to the next slide. We can see here that the IonQ image that we passed arguments very similar to the previous one, where we'd pass ones and zeros, and for a given row, and we would then move to the next one, and it would give us this image for the perfect information state that the IonQ target provides. We then moved on to Quantinuum, which is a little less lossless, and similarly, we were provided with another such image. And interestingly enough, due to the noisy nature and density of entropy going on when each when one pixel is passed to take argument that there is a two-state system, and moves on to another pixel, it then creates this this arbitrary function due to all of the extra heat that goes into adding all these Hadamard gates that we then measure to have some given speed up for this specific algorithm. What is going on is we have bit shifts going on for piecewise for these piecewise functions, and rotations. We have rotations and translations occurring over our given superposition of two states for a one qubit system. Had we more time, we would, of course, use a 4x4 matrix in order to better represent the sort of Gaussian distribution that occurs with a certain given number of weights. However, this does poignantly explain just how fast 1,000 gates can operate on a 8x8 image. And this is what we got back, and this happened in 12 seconds, which I think is not bad, provided it practically cost us a cent, just about a penny on the credits. And moving forward, so as you can see, we came to this conclusion for the Amazon by assuming that the number of gates for a given 8x8 image had the same number of operations occurring with our given basis case, the ON time. So when you take the 64 bits, the 64 pixel image, and assume it to be linear, we then use that. Sorry, for the 8K image, we used the linear basis case to divide over the 64 pixels that were used for our computation, and we noticed the equivalent to using these gates, even if it did cost us 1 cent, also means that a similar equivalence by means of just looking at the sheer number of pixels as it operates over some given set. In this case, 8,000 divided by 64, we get about half an hour, which is just a little bit less than 17 cents. So we found it to be financially very effective. However, computationally trivial due to the complex nature of the gates in general. And the reality of lossy information really goes to show that as it pertains to entanglement entropy. So through comparing the superposition circuits with our Hadamard gates with respect to the Turing machines, we then found that there were noticeable differences in the computational speed up. It took a 64 CPU ARM processor tailored to machine learning in order to find a comparable time of 17 seconds to that of a 12-second 1 qubit system with many different operations occurring. Such an analysis is it would be necessary to look at further analysis of that because of its sheer sporadic nature. I mean, it is stochastic in nature, I suppose. But those are our findings, and thank you very much for allowing me to present on this. I thank you for my team for working so very hard on all of the different parts that created this this Gestalt project. That's it.
Fantastic. Thank you. Yeah, I appreciate how exploratory and ambitious this last project was. And I want to express how impressed I am with the results of the challenges and those people who presented today and all those people who didn't present. I noticed that there were, a lot of people made presentations and didn't end up sharing them today. And a lot of the GitHub READMEs I saw were absolutely fantastic. And I can't wait to go deeper into these projects and learn more about what you guys have created. All right, well, thank you so much. This is, we have the opening address, the closing address at 5 Eastern time tonight, but you can tune in later on Twitch that will be broadcast. And that will conclude the hackathon later. So thank you so much for being here. And thanks again to our presenters for taking their time to present today.
Thank you, sir.
Thank you so much, Ben.